In this tutorial, we shall continue from the previous part of our video to explore various settings within the color window in detail. At Colors window, each color stands for a material or a surface boundary condition depending on the input at color type. In the previous video, we have seen how to toggle from one color type to another by double-clicking the cell. In this flow chart, we see various inputs under types categorized as per their thermal property. Material under color type is used to define the conductive medium. In most cases, we input solid materials in the layer stratigraphy as a material. Whereas cavities or boundary conditions have convection and radiation as primary heat transfer mechanisms. We will discuss in this video later what's simplified method and the radiosity method. We will now zoom in on each available Physibel type in relation to the color window. The first type, material, is for a conductive medium. At Physibel, we can easily specify material properties using a color database, and you can also find the conductivity values linked as per ISO standards in this color database. At the color window, under the type material, we can input the conductivity value for a material and choose to edit or rename the material name if required. When used in a project where detailed radiation is used, for example, transmat or BC-free, the column emissivity also becomes available. Here you can input the surface emissivity value under material. How we work with detailed radiation will be explained more later in this video. Next type for cavities and voids are equimat, transmat, BC-free S and BC-free. For the first two types, equimat and transmat convection is treated as a conductive medium. An equivalent thermal conductivity is calculated as per ISO standards. For the latter two types, BC-free S and BC-free convection is modeled with one convection node, which assumes perfectly mixed air. This is typically used for bigger cavities, say bigger than 300 mm. The difference between equimat and transmat is the way infrared radiation is treated. For equimat, infrared radiation is simplified and equivalent conductivity, which is the lambda value referred from ISO standards. Here we input equivalent thermal conductivity, which includes the combined effect of conduction, convection and infrared radiation. Whereas transmat is a detailed approach, we calculate detailed infrared radiation. This approach is called the radiosity method, where we consider the real geometry and surface emissivities which are defined now at the material level. Hence, in such cases of performing analysis using the radiosity method, emissivity input is enabled under infrared radiation. We have seen till now the approach to model heat transfer through smaller air cavities with equimat and transmat. Now, for larger cavities, say for example more than 300 mm, it's more practical to model the air space with one central temperature node, assuming perfectly mixed conditions. Here again, we can distinguish between a simplified method and detailed radiation via view factor for infrared radiation. The type BC-free S considers simplified infrared radiation. This means that the cavity is modeled with one global temperature node connected to the cavity's surfaces via a global heat transfer coefficient H, including the combined effect of radiation and convection. The type BC-free, on the other hand, considers a convective node temperature in the cavities, linked with a convective heat transfer coefficient Hc to the surfaces and detailed infrared radiation via view factors across the cavity. Here we see an example, where rooms are modeled as BC-free. Similarly for boundary conditions, for a simplified approach, we choose BC-simple. Here we combine the effect of radiation and convection between the environment and surface as one global surface heat transfer coefficient H. This defines the heat transfer from the surface to environment temperature theta. Whereas BC sky allows taking detailed infrared radiation into account through view factors. The type BC sky allows to differentiate between convection and infrared radiation. Convection is defined via a convective heat transfer coefficient Hc. For radiation towards the environment, one should define the radiation temperature of the environment, theta R. The example on the left shows the use of BC sky to model the undercooling condensation caused by the outer side of a skylight during clear sky night conditions. BC sky is not just used for exterior boundary conditions. In this example towards the right, we place a coffee pot with a low-E surface near the window and see the reduced heat transfer towards the window. Here we input the indoor boundary condition as BC sky to perform a detailed radiosity analysis. Hence, to summarize, for all solid materials, conduction is the primary mode of heat transfer. We choose the type as material. For cavities where convective and radiative heat transfer is possible, we choose type equimat to consider simplified radiation and choose type transmat to perform detailed infrared radiosity analysis. For larger cavities, which is in size of a larger void or a room, we choose type BC-free-S for simplified radiation and BC-free for detailed radiation. For boundary conditions, we choose BC-simple with simplified radiation and BC-sky for the radiosity method. We hope now you can clearly distinguish when to use which type during analysis. Thank you for watching, see you in the next video.